So guys, let us start with the topic of elasticity. And about elasticity, we are going to start by writing the definition. We can say it is a property. You can write that a property, so elasticity, for understanding sake, let's start with definition. Elasticity is a property of a body to return back to its original shape after it has been expanded, or you say deformed. So the property of an elastic material or a body to return back to its initial position when it has been deformed, that we call an elasticity. And we might have studied in our early classes that about elastic body, there are some limitations and some other things that do affect the property of a wire. For example, you consider a wire when it has been stretched, and it has a tendency to go back to its original shape or size. So any property of a body that behaves in this form after deformation, having a tendency to come back to its normal position, such body is said to be an elastic material. Another note we can put down here to understand this is that you can also write, because we need to understand that there are different types of material, which I believe, in early classes we might have studied. Now, when we talk about material, we have different classification, especially in our chemistry lecture class. When I've talked about, we have wire has different properties like malleability, ductility, and so on and so forth. I believe we have an idea about it. But to understand this better, when we say elasticity, we are talking about, we can say it is due, I think it is also important to put it down, it is due to intermolecular forces. Intermolecular forces between the constituent particles. So when we talk about elasticity, we are talking about intermolecular forces between constituent particles, and that is why rubber can expand and other things can also expand. Now, let it also be told to us that there are some material, that is talking about classification of materials now, that do have the tendency to expand partially. So I will also introduce us to what we call partially elastic body, because of definition, which is also required in our syllabus. That is why we are looking into it in every areas in which question can come. Now, elastic body can be deformed, and after it has been deformed, they return back to their normal position. Most especially, you know what we say wires, for example, ductility of wire. That is ability to stretch, which you all know. And malleability, you should know malleability can be hammered and so on and so forth. But what I'm trying to say here in terms of elasticity is that it is not only wire that can be, or rubber that can be expanded. There are some other materials that can also be that can also undergo the process of elasticity. But we classify them as a not perfectly elastic body. I hope you understand what I'm trying to say. That is, we can also classify elasticity not only into what elastic material and non-elastic material. There is also the ones we call what partially elastic body. And let us write definition to that because of what examination. We can also write, we have a partially, or let's write it partially elastic body are those that do not return to their initial position after it has been stretched. That do not return fully. Let me put that do not return fully. Let's change this so that we have a good definition to their initial position when they have been stretched. We can look at some physical example with our home experiment. We can try it. There are some material that when you actually expand them, when you apply force to them, they will not return back to their position. They will return back, but they can never regain back their fully shape. Such bodies are said to be partially elastic bodies. Then again, when we now classify the third type, which we call the rigid or, I want to say rigid or plastic bodies. You can say, are those that resist, and just define in your own way. This is why understanding is perfect. That resist the application of force. Or you say that the body or bodies that cannot be deformed. I think this is better. That cannot be deformed. So when we say classification of bodies, definition of elasticity, elastic applications, talking about elastic material, partially elastic material, plastic material, or inelastic material. Now, let it be known, when you say inelastic material, which is the last type that I want to talk about, they are also different from rigid bodies or plastic bodies. We need to understand that. Now, when you say rigid body, those ones that resist is when you try to push something out to change the deformation of a material, those particular ones that cannot be deformed. You should also keep this in mind that in nature, we can say in nature, there is no such bodies. That is, you don't have body that actually totally resists the application of force when force is applied to them. But we say in definition, we don't have a particular body that exhibits that kind of 100% that kind of features. So, but in definition and in application of physics, to understand definition very well, we say plastic bodies, or when we say rigid bodies, are those ones that resist the application of force, or those that resist or that cannot be deformed when force has been applied to them. That is why I said it is better to use the second one, the latter, rather than the first definition. So those that cannot be deformed by by application of force. So you can't say they resist application of force totally, because you can apply force to them, but they will not be deformed. I hope I'm communicating with all this. Now, to understand the last type of bodies in classification of body and introduction to elasticity, we are going to also define what we call an inelastic body. So we can also put a note down that saying inelastic bodies are those that do not return back to their shape after it has been deformed, after it has been stretched or deformed. So students should keep this at the back of your mind, as inelastic body are quite different from what you call partially elastic body. So because I told you, partially elastic body do not resist application of force. You try to you apply force to them, they get deformed. They now want to regain back their position, but they will not actually regain back the position 100%. Such bodies are said to be partially elastic. But in the case of the other type of bodies we are talking about, which is the inelastic bodies, such bodies are those ones that when force is applied to them, they are going to be what? Deformed, but they don't want to come back to their position. Example in nature are many. Let me just give you some. You can just think about a very good example that is coming to my mind is clay. Everybody know clay soil. Yeah. When you try to what? To apply force to clay, you can see the shape of clay is going to be deformed. Then what? It can never what? Come back. It doesn't have the tendency or the ability to come back to its initial position. And such body is an example of what? Inelastic body. So let's keep it in mind and not to make mistake as we proceed in the topic of elasticity, that we have classification about rigid body, plastic body, elastic body, partially elastic body, and inelastic body. These are the classification we give in physics to type of bodies, and these are needed to be known by students to avoid error in definition and also in application as we proceed. So let us get to the next slide to see what we have to explain. Yeah, fine. About the next slide in sequence, we have to explain another type, another important factor or concept under the topic of elasticity we call stress, strain, and its type. Now, as we have already studied that when a force is applied to a body, we can keep down a note. When a force is applied to a body, when a force is applied to a body, it changes not only the size or the shape, it changes the size or the shape, which we call the body gets deformed, right? Which we have studied in the previous slide. Now, whenever the force is applied to a body, it changes its size, or the body gets deformed. And if the body is an elastic material, is an elastic, or has the elastic what property? Is an elastic material, comma, it will have the tendencies of returning back to its initial position, as discussed. Now, what I want to bring about here now, guys, from this definition, which is synonymous to what I have said in the previous slide, is that means a force was applied to a body and the body gets deformed. When it got deformed, being an elastic material, it comes back to what? It has another force. That is what we call restoring force. And this is where we are going. Now, students should understand that when we talk about stress, when you apply a force to a body, the body has been stressed. But when we talk about stress, students should understand that there's a difference between when we are talking about internal force, because the body was stressed. That is why it got what? It got deformed. So then it will now have another force, which is the restoring force for that body, provided it is elastic, to gain back its fully shape or size. So the restoring force that is what acting within the a particular area, which is the particular area in which the deformation is being carried on, is called a stress. So we can write now, in continuation to what we have written down, that again, another important point we can put down is that the restoring force, which is the internal force. Students should keep it in mind that when we talk about stress in definition, it is the internal force that is acting per unit area. So it is not external force. That is another thing you have to always give a back on, because most of us do make mistake that it is what? Force per unit area, fine. It is not the one that was applied at the beginning, but the one in which it is taken to get back to its original position. So we can put this down that what? The restoring force acting, because acting perpendicularly, because it is normal. The restoring force acting perpendicular, or let's say the restoring force for now, because we are still going to talk about the types to understand it very well. The restoring force acting per unit area unit area of a body, or bodies as the case may be, is called its stress. So we can keep that at the back of our mind for now. And it is expressed, we can say the mathematical interpretation to stress from early classes you might have studied is that stress is given as the what we said internal force or restoring force acting per unit what area. That is the area in which that particular substances of body has been deformed. So I hope you understand the interpretation, because physical situation can be performed at our various forms to understand this very well. And that is why I'm trying to illustrate by gesticulating. So another thing we have to keep in mind that when we talk about stress, we have types of stress. Now, basically in physics, we have two types of stress. Let us always keep that as a third note as well. We have two types of stress. For our level now, there are two types of stress. Excuse me. So we have two types of stress. There are two types of stress. For our examination, we have to keep this in mind, and we are to be able to explain each of them. The first type of stress is called the normal stress. Normal stress. Normal stress. You can see when I was to define the other time, I want to use the word perpendicular. But later I got to realize that I'm still going to break down type of stress for you. That is why I keep it to myself and not what refuse to put word perpendicular. Then the next type of stress is called the shear stress. Keep it at the back of your mind, as this is also very, very important for you to know and to define. Now, when we say normal stress, students should keep this at the back of your mind, because we still have to talk about strain, and I'm doing everything on this slide. Another topic is on the other slide, so I have to keep my word explanation. Just listen to my voice, and I hope I'm not too fast with what I'm doing. Now, normal stress. When you say normal stress in physics, when you say a stress is normal, the word normal means perpendicular. So what we're saying is that if the direction of force is acting normal per a particular area, so such force is defined as normal stress. I hope you understand that you've written that. And if you want me to recapitulate, I said when a force is acting normal, a very good example, I can show that at one side here for understanding's sake and for us to understand what we are talking about. We have something like this. Let's take this. Wow, coming. So let's say we have a good illustration should be better like this. We have a block of mass M, that is always my weight, and it's resting upon what we have on the ground. As you can see, this is the block of mass M. Then a force was applied normally. When you say normal, normal is what? You can see normal means perpendicular. This is the direction of force. Was applied to the body. Force is a vector quantity. I'm putting an arrow on top. Because of this force that was applied normal to the surface of this block, what you expect to see is that what there will be a deformation. So now the deformation has now changed the direction of or the length of this bar has been deformed slightly, let's say to this point of red that I'm trying to show. And you know, if the body is elastic, there will be another force, which we call restoring force, that we also act in what opposite direction. This is the other restoring force. Now, the block is having a surface area of A. I hope you are following. Surface area of the block is A. And we can say now that the normal force and normal stress acting on this one can be given numerically or mathematically as normal stress. Normal stress is given numerically now as what we call the normal force per unit what? Per unit area. I hope students understand this. And this is the definition we give to normal stress in physics. The other type of stress we call shear stress. Students should be careful about when we talk about shear stress, we have to understand another thing. Now, it is just opposite of this. When we talk about motion and now when we talk about free body diagram and other things we have learned under the topic of mechanics, the way we call it in physics, we have studied a lot of direction of force and different angles at which force can be applied on the body. The same thing is what we are actually using here. Normal means perpendicular. But when we talk about shear stress, they are the type of stress that is exhibited in an elastic material such that the direction of force is acting tangentially. Remember, there are two types of force. We have normal force and we have a tangential force. Tangential force is horizontal, normal force is vertical. This is the way we have explained resolution of forces time and time again in our physics series. Now, for now, to understand shear stress, we are saying they are what? They are tangential force acting perpendicular or acting tangentially, tangential force acting horizontally per unit area. To understand that very well, I hope you are keeping that in notes, which is very, very important because of definition and understanding of all this stuff. Now, to get that very well, my dear students, we say shear stress is now defined as what? Directly we can say is a tangential force per unit area, which is better per unit area. To understand that also very well, we can also look into a physical situation, which I will try to draw out for us to get very well. Let's say we also have the same block, diagram not drawn to scale, just for understanding, that is resting on ground. This is a block resting on the ground. There is a block and there is a ground. Now, in this case, we are talking about force was applied in this direction. Let me change the color of this for us to see clearly. The direction of force applied to the body was in the horizontal direction. As you can see, my dear student, this is the force that is applied to this body. We have force. The force is coming tangentially. And because this force comes tangentially, we can say or conclude that there will be a deformation. Let's say there's a slight deformation here, and they form this block in this direction. As you can see, the deformation is now giving us something like this, as you can see. Now, we say directly, you can see it is now acting at an angle of theta between each other. This was the normal block before, but because of deformation, it has changed its size. It has increased its size at an angle of theta. So this particular type of force over, well, let's say the area covered by this thing is given by A. So directly numerically, we can say shear stress is given by formula. We said that the what? Tangential force divided by area. So students should keep this formula at the back of your mind, as we are going to be using it directly to solve a lot of numerical under the illustration centers. Tangential force acting per unit what? Area. Now, again, we can also bring a physical situation whereby these two types of force are acting on a single body. Yes, it is possible. I said we have two types of stress. Normal stress when it is acting normal, or you say when it's acting perpendicularly. Anyhow you want to put that is accepted. Then the other type of force we have also just stated now, shear stress. We said the force is coming narrowly horizontally, which we call tangential. Tangent is horizontal. Let it be known. Now, when these two occurs on the body, you can resolve it into components, just like what I have explained here the other time. If I want to put another type of force, we can put the second one coming downward, and because it's coming downward, we know too, it is also going to change the direction of what it will deform it slightly by a distance of whatever. So at this point now, you can say you have two components. One is F sine theta, and the other is what? F cos theta. So this is the way we relate that in physics. And please don't be scared when you see questions. That is why I'm trying to narrow down the concept. I want you guys to understand concepts before you tackle question. But without concept, questions, you can't just be using formula when understanding is not thick. So about the next one, we introduce ourselves also on this slide to strain. So about that, let us quickly put down in notes. Like I said, everything must be narrowed down on this slide. So directly, let's say we want to write about strain. Let's give definition to strain. As we have studied that when a force is applied to a body, or what I'm saying is that force is applied to a body, the body will get deformed. Restoring force will take it back to what? Provided it is an elastic material, the restoring force will take it back to its normal position. So now, when force is acted to a body, we said the body has been stressed. Now, as a result of this stress, there is the change in shape or change in size, or you can say change in dimensions generally. So when there is a change in dimension of a body as a result of stress, this change in dimension of body as a result of stress is called a strain. I hope students understand that. Let's put that down into writing. We can say the change in dimension, for a short note, the change in dimension of a body as a result of stress is called its strain. The change in dimension of a body as a result of stress is called its strain. As we have also discussed about different types of stress, we are also going to talk about different types of strain. Now we have strain types, and in physics classification, we classify strain into 3 types. So now to understand before we move to that, I think to give you what the numerical interpretation to strain. Now to understand strain very well, I don't want to overrush, though I am racing against time as usual. Time is always a major problem and a constraint. So we just have to need to know how to work about that. Now, as what I'm saying, my dear students, you have to get something here. When we talk about strain, it is expressed numerically. Let us also write that. I think is important. The numerical interpretation of strain is given as a strain is given numerically as the extension produced by the body, that is the deformation produced, divided by the actual length, or you say the original length. This is the way we relate that actual length in physics. So guys, you can ask me how do we come about that, because you know I love proving. Yes, fine. We can prove that. Now maybe we have a dimension, but before I can prove that, I think it will be better for me to explain type of strain. If I explain type of strain, then when I illustrate each of them, you are going to see what I'm talking about. Now in physics, the classification of strain are in 3 types. I hope I'm audible. Now there are 3 types of strain. The first type of strain, which is common everywhere you go, is called what? We have the classification of 3. Strain are classified into 3. The first one is called longitudinal strain. Longitudinal strain. Now I'll be taking them one by one, and I'll be explaining it directly for understanding. And when you say longitudinal strain, from the word longitudinal, we are talking about the change in dimension of length. So strain that occur as a result of change in dimension of length is called its longitudinal strain. To understand this carefully, let us take a particular one. Let's say we have a rod that is fixed at one end. When I say fixed, I mean clamped at one end, and before the size of the rod was this. Please watch, my dear students. And as a result, well, let's say the rod is having a length of L, as you can see, and it's having a particular it was now a force was applied in this direction. Look at the direction of force in this direction. That is the force. The force was applied in this direction, as you can see, dear student. And because of that, there will be a change in size, as we might have studied. As we have studied, not we might have, we have already studied now. Now we can say there is a change in dimension, and the change in dimension has brought about the extension, which I want to use a green color to show. Now it has now been increased. The formation size as a result of stress, which was the force, it has now been increased by a distance of what? Let's say distance of x, or you can say dx, data x, or you say x. I love using data x. If you are conversant with my videos, you see that I am familiar with what data x. That is my way. So you can use your own. It's not only x that you have. So now what you can see now is that this particular body has been strained by by a distance of delta x. So we say the total strain acting on the body, from what I'm saying here now, is the change in we said the extension, the change in the length, which is delta x, according to what I'm showing here, divided by the actual length of the rod before the application of force was L. So this is the type of strain we call longitudinal strain. In fact, I do tell students that when you want to define strain, the direction of force is not only going to be sometimes it is not only when you expand something that it is going to be strain. In fact, when you try to compress, you can also have strain, because if the direction of force is inward, what happens? The length will be shortened. So that is why we say when we define strain, we call it extension. It is not always it can be forward extension, and it can be backward extension. So the extension produces the change in the extension in the direction of force. Are you getting, as a result of the stress? Strain, it comes as a result of stress. So strain is a subset of of stress. So that is another important thing you just need to keep at the back of your mind, and that's we call when you are talking about change in the dimension as a result of change in in length, you are talking about longitudinal strain. The second type of strain, we can quickly put that into writing now, is what we call please students need to understand this, is called bulk. Please, you need to understand we have bulk Or maybe we should talk about shear strain before we talk about the last one, because the shear strain, you've heard about shear stress. We also have shear strain, which is also important. Shear strain, which is also important. Now, as we have studied under stress, we said that when the force is acting tangentially per unit area, the particular force acting tangentially with respect to the area of that particular shape, that's one word that has been deformed, is called what? It's called a stress. The same thing is applicable to strain. We can say what? It is a tangential force that is acting. Now, when a force is acting, a tangential force acting on a body, excuse me, and the force we are talking about has brought about the change in what? In dimension. So what we are trying to say now in terms of this type of strain is that when the direction of force acting on the body is coming tangentially and now bring about a change in dimension, that particular type of strain is called what? A shear strain. So let it be known by student. Now we can also explain that the way we've done this. Let's take the same diagram we used the other time. We said we have a body like this. The body was acted upon by what? What type of force? It must be what? A tangential force. Diagram not drawn to scale. This is a tangential force, and the tangential force acting on the body has caused what? Deformation. This is the force F as usual. Then it was deformed, slightly deformed like this. And because of the deformation, we have a change in what? You can say there's a change in what? This is the angle. Remember, angle here is theta. And we say this is the height before, but now you have what? The distance in which it was deformed, we take as x. So directly we say shear strain. You can just write numerically, shear strain is given as what? You can see that is given by the dimension, that is the extension. It was extended by x. The original length before is given as what? As h. So what we are trying to say here, my dear student, if you join this place to this place, you understand what I'm trying to say. That is how we come about the extension and the original length. So extension divided by the actual length is always strain, but it depends on the direction of force. If the direction of force is tangential, we call it a shear strain, and it's given by x by h, which is the same thing as theta. Please keep that at the back of your mind. You can say, I said the angle acting between F and H here is theta. So it's always taken to be equals to theta in physics. Keep that at the back of your mind. It's very, very important in applications and numerical. So it's taken even as theta for a value of what? For a small amount of value of what? Theta here is a small angle. So when we say the value of the what? Of the strain is small, that is when we consider what? X divided by H to be equals to theta. So numerically, you can say theta is the formula for shear strain. That is where I'm going. And the third type of strain, which I think we need to talk about for us to feel that there are three types, is called what we call the volume. Some people will say volume strain, pressure strain, volume strain. Yeah, volume strain. When we talk about volume, everybody knows that these are what the types of dimension, the change in dimension as a result of change in volume of a gas. So it is always applicable to what? To a gaseous substance or fluids, liquid and gaseous substance. As a result, we can just take a simple example. The simple example I can give to you here for understanding is my way of doing stuff like that is drawing out a bucket that is filled with water. This is a bucket was filled with water to a particular level, as always. Then because of the force that was applied to it, strain is a subset of stress. There is a change in dimension, which I'm going to use a color to show. The dimension now has now what changes what? It has now come to this side. So the change in what? In what? This is the new volume. The initial volume was V. So you say the change in volume, volume strain, you can write that volume strain is given directly by formula as a change in volume divided by the actual volume of this. And this is what? This is the definition we give to what? Volume strain. So keep this at the back of your mind. As we move forward in this topic, you might be tested in numericals on how to solve a question using all these formulas directly. So it is not only the illustration you can give to it, you can also think about in terms of pressure too, because if you have a gas that is having this, and it was compressed as a result of pressure. And this was the initial pressure. This was the pressure of the gas before. Then because of pressure, this was the initial volume rather. And because of what the pressure applied to it, this was the change in volume. So this is another illustration that can be given onto this, and which bring about the strain happening in this body to be a change in the volume divided by the actual volume. I believe all these are studied in early classes, but because of maybe some of us that are not actually so good in understanding the concept, that is why we are trying to break them down as we can for level of understanding to increase. I hope you understand this. I said we have a shear, longitudinal, and volume strain. Keep it at the back of your mind, and keep the important formula at the back of your mind too as we move in sequence to the next slide. Yes, about the next slide, we have a relationship between stress and strain. And to understand this concept very well, we are going to introduce ourselves to what we call the Hooke's law. Now, and about Hooke's law, for understanding of concept very well, it is as a result of experiment by Robert Hooke. And the experiment, in conclusion to his experiment, it was stated that provided the elastic limit, because of some of us that are still doing theoretical examination, provided the elastic limit is not exceeded, elastic limit is not exceeded, then the stress is proportional to its strain. Now, as you can see from what we have just discussed about that, elastic limit must not be exceeded. That means there is a condition before you can say the stress acting on the body is equal to the strain or is proportional. It's directly proportional to the strain. There must be what? A condition. And the condition is what? It must not exceed elastic limit. The strain must be very, very small. It must not exceed what? Elastic limit. And please, these are things you need to keep at the back of your mind before we start relating it experimentally. And if you can look at what is showing on your screen now, the picture that you can visualize, you can see very well as a result of Hooke's experiment. According to him, this was what, when he tried to plot a graph of stress to strain, the following diagram was brought out according to him in that year. Now, about this now, the graph of stress is plotted, as you can see, on the vertical axis, and the strain is plotted on what? Horizontal axis. From what we have stated now, what we are trying to say is that the higher the stress, the higher the strain. Mathematical interpretation can be like saying, we are saying the stress, the proportionality constant is proportional to strain. This is what we have stated from what we call Hooke's law. And this is only applicable up to a certain point. Now, to understand this critically, I'm going to be showing all the labels and the definition to each of the points according to Hooke's diagram. Now, directly now we can see we have point A, B, C, D, and E on top of this. And if you look at the graph very carefully, it can be inferred from this graph, it can be concluded that if we look at it, the graph is rising up to a certain point. This is the simple experiment we do in our junior classes. That is when we are going to talk about placing different mass into a spring. Are you getting it? I hope you are following. And when you try to place the mass into a spring, you are going to see as you increase that particular mass, the extension will also be growing. If the extension is like this before, as you move, you see the extension will continue increasing until a certain point. You can see until a certain point, it increases up to a certain point here. And this particular point of increase, that the higher the stress, the higher the strain, is called the elastic limit. Let it be known that the highest point at which a material can reach when it has been extended, that is when the stress increases, the strain also tends to increase. That point is defined as elastic limit. So here we can say point A, according to our diagram, is called the what? Elastic limit. So that's the first point. Now, Looking at the next point, you can see as we continue to increase this, you can see the moment we continue to increase the stress, this is the value of the stress, we increase the stress above this limit, this continues to what? Increase up to a particular point whereby the value of the increase in stress is no more increasing this particular what? The strain. The point at which an increase in stress will not bring about any increase or decrease in strain is what we call the yield point. So what I'm saying, my dear student, here is that point B here is just the point immediately after the elastic limit, whereby the increase in stress is not going to bring an increase in in strain. Because what we are trying to say, or we say the point, I think this is better to define for some of us that we are not so opportune to know all these things before. We say point B, according to my definition there, is called the yield point. The point is called yield point. Now, again, I said you can also define this point as a point at which the wire or the spring or whatever, the elastic wire cannot regain back its shape because it has exceeded the elastic limit. That point in which the wire can never return back to its shape as a result of maybe because it has now been plastic. I'm getting it, plastic. We've talked about plastic. The point is called the yield point. You can keep down a note on this. It's also very, very important. Now, the third point is called, we have to see, and again, the definition to this particular point this is point C. You can see, as I increase this after the yield point, if you watch very well, as I try to increase the value, this is the yield point. Now, if you notice something, a further increase in this thing will not change anything again. So at this particular point, just after the yield point, if that you can see here, we call this point of what? Proportionality. It is not that common, but you need to understand that what it is just immediately after the yield point, we have another point we call the proportionality point, which is see here. It's called the proportionality point. Directly, I can define this point like what I said the other time. I said the point at which the material cannot go back to its particular shape immediately after the yield, but the elastic limit is called yield point. Now, proportionality point is just a point whereby an additional increase in stress will not bring about an increase in strain. This point we call proportionality point. Keep that at the back of your mind and see its place. That is the proportionality point. Another thing you can keep in mind about this is it is just immediately after the immediately after the yield point. The next point is the point we call the maximum stress. It is also important to keep this at the back of your mind. This is called the point of maximum stress. I hope students understand the meaning of stress. We've talked about stress because this is the highest level at which the stress can reach if you continue to increase the stress. Any other point after the maximum stress, what you expect is for that particular wire to break. And this point, sometimes you can use a broken line to represent E, and it's called the breaking point. I hope students understand the definition I've given to each of these points, and we can write D for writing's sake as the point of maximum stress. As you can see, that is the highest point of stress in the diagram, maximum stress. So immediately after that, if you try to there's nothing you can do again. The next thing after the maximum stress, you are going to see that the material starts breaking. The very good example is rubber band. If you try to expand the rubber band to a certain level, you can see it will still be expanding. The moment it exceeds the elastic limit and it crosses over the yield point, you will see that the material can never regain back or return back to its shape again. The next thing you see is that you start seeing gap between the rubber band. That point you start seeing gap, you said that particular point has been marked, something like it has been stretched, and you have a mark. That particular point is called the point of its maximum stress because it has been stretched beyond the limit. So again, it has passed the yield point, the proportional point. Now it has at the maximum stress because any further force applied to it In fact, you don't even need to apply any force at that particular point. The next thing immediately is what? Is for it to break down. So do not make a mistake in understanding this concept. Be careful about proportionality point, because what we call proportionality point is that no force is added to it, as in if you add force to that particular body at this point, you can see the direction of the force is having what is more or less like a straight line here. This point, it can never return backwards. It's what shape. It can't return back because it has passed its what elastic what limit. This is the definition we give to what to that. And I hope you understand the way I've broken this down. And to understand this very well, guys, my dear student, I am also going to what talk about the numerical aspect in the later part of the of our syllabus, or under this topic of elasticity. Now, let it also be known that the numerical aspect of Hooke's law, we can also quickly talk about that on this slide to finish this particular topic in a better way. And we can say directly that from Hooke's, we said he said the stress is equals to provided elastic limit is not exceeded, the stress acting is proportional to what? To strain. And in the spring that we can also write that if stress, let me just say the numerical aspect is directly proportional to strain, we can say if we now want to say stress is equals to strain, there will be a constant of proportionality. Don't mind this camera. Let me try and adjust for you to see me clearly. Now, the constant of proportionality that comes between stress and strain is called E. And E for now, I will let you guys understand, is now called modulo or modulus of elasticity. So let us always keep this at the back of our mind, that the modulus of elasticity is the proportionality constant that relates what? Stress and strain. About modulus of elasticity, we are going to talk about it in details in the next video according to the way this video section has been planned. Understand that the modulus of elasticity mainly determines the elasticity of a material. So, and you can actually relate that by making that sort of formula and say it is equals to the what? Modulo of elasticity. You can also write modulo of elasticity is equals to the stress. When you make a sort of formula, the stress divided by its strain. So keep this at the back of your mind. And let us also not forget to talk about the other aspects apart from stress and strain. We know the stress is a force. When you add force to a body, it is what another way you can relate this, because of those that are in junior classes, is that the force, which is the stress, is equal to the extension, which is the strain. And if you want to go by that, numerically, you can also say F equals to constant, you say KE. This is junior classes. You remember this under the aspect of your spring. Now, don't forget K here, you said is called a force constant. So all these, I believe we might have learned in early classes. And if not, I have tried to summarize in the fastest possible way in which I believe we should be able to get. So guys, keep this in mind, because all these are going to be needed when we start the full illustration. And for this topic now, I'm going to stop here for the first video, the continuation of type of modular of elasticity and some other facts we need to know, as well as the energy stored in wire, are going to be in the second slide of the video. So I will check if the student were able to prepare some slide for us to do some illustration, which will be the last aspect of this topic. Fine. We have some illustration here, which I will take very quickly. Now, about the first illustration, my dear student, the question says, the diagram above represents a stress and strain graph of a loaded wire. Which of this statement is correct? We say at A, the wire becomes plastic. At A, the wire did not become plastic. It is at B, it will become plastic. I told you about that because B is the yield point. The second one says B is the yield point. Yes, we have D is the elastic limit. B is the yield point is correct. D is the elastic limit is very wrong. You know about that. At C, the wire break. That is very wrong. So the correct one is B is the yield point. I've already stated that, and I believe we understand why the answer is choice B. B is valid, and that is the question answer. The next one says the point at which the molecule of a loaded wire begin to slide across each other, resulting in a rigid increase in extension, is called dash. Now, because it is rigid body, that means where no more force can take it back to its point. You know, I talked about proportionality point. So we should be very careful about proportionality point. There is a difference between rigid body and what we should be very, very careful, please. I have reasons for taking my time to explain all these concepts. The body cannot return back to its original shape. That is heat point. Immediately after the heat point, you have the proportionality point, where the body becomes very rigid. So be careful about this because the wires slide over across each other, resulting in a rigid increase. So at that point, it is just immediately after the heat point, when the body has been cannot go back to its original position. So note that, please. So now here, the question is so technical. Molecule of loaded wire begin to slide over each other, resulting in rigid increase in extension. You can say rigid increase in extension. The extension becomes increase. So be careful about that. You're going to be B here, and that is valid. So please, that is that about that, my dear students. We'll go to the next one. If there is another slide, okay, fine. Now, the point beyond which a stretched spring does not return to its position is called the elastic limit. So guys, about the elastic limit or elastic point, you can see there's an error according to the student that prepared this slide. One should be elastic limit and not an elastic point. Please keep that at the back of your mind. And this is, let's say this is elastic limit. That is why you need to know the concept. Then the last question, I think, she actually put a numerical under this slide, and we have one. So the last question is the total length of a spring when a mass of 20 kg is on from its end is 14. Fine. The load actually acting on it was a 20 kg load, or used to convert it to Newton in terms of force. Then while its total length is 16 when a mass of 30 is on from it, then calculate the unstretched length. You know, we can quickly do this directly from what we have just learned not too long. We say solution to that, we can just bring a length. The initial length was this. So we take that as the initial length of the wire. I'm taking that as L. Then a load of something was on from it. When a load of something was from it, I'm sorry because of time, I've exceeded the time. A load of 20 was on by this. This is the last question for this slide. Load of 20 kg was on from it, and the centimeter was 14 centimeter. This one has a zero load. We can say 0 kg. I hope students understand this. These are junior questions, which I believe you might have studied. Another one says a load of the second load was said to be, what is it? While its total length was 16, when a mass of 30 kg, she had made a lot of mistake in preparing this slide, and we don't know what has come over her today. So this will be 30 kg, I presume. So that is 30. The length is now 30. You can say L of 2, or L2 is 30 kg when the load of what was 16 centimeter. The question asks, calculate the length of the unstretched. So let's just do, we know that load is proportional, force is proportional to what? Extension. Force is load. Mass, this is fast, this is it, and the extension at the length. So I can just relate by saying, okay, if I have that, make case of a formula, you have F1 by E1, early classes, is equals to F2 by E2. This is the formula you set. Numericals are very important. That is why we do illustration at the end of every section. So the first load, I'm taking the first two, comparing this, I will say 20 minus 0. See, F1 is 20 minus 0 over E1 is 14 minus L. I hope students can see this. Is equals to the F2 is now this and this. 30 minus 20 is going to give me 10. And I have 16 minus 14 are 2. 2 can divide 10. 2 can go in 10, 5. We say 20 over 14 minus L is equals to 5. I hope students understand this. You can go by your cross multiplication and finish up this. By cross multiplication, you have 5 is equals to 14 minus L. As in 5, we open the bracket is equals to 20. I don't want to remove the bracket because 5 can go in 20, 5 here 1, 5 here 4. So directly, I can now say directly that L is equals to, I hope students understand what I'm doing, 10. And if you have issues with that, you can always tell me. You can see the length will be short when there's no load. When the load was 20, it's increased to 14. When the load was 30, it's increased to what? This is because load is proportional to extension. Force is proportional to extension according to Hooke's law. So this is where I'm going to stop, my dear student. See you soon in the last part of this topic before we call it all, or we say bye-bye to elasticity and its property. Bye, and do have a wonderful time.